Step number 4, to plot root locus. In this step we have to figure out where does the locus cross its imaginary axis. Now remember, when the roots are going to cross the imaginary axis, at those points the system is going to become critically stable. Anytime you have single roots on the imaginary axis, the system is critically stable, and if you have repeated roots on the imaginary axis, of course system is unstable. But in this case, we will basically evaluate when the system is going to become critically stable, and then figure out what will be the values of k for which the system is going to become critically stable, and those points will be the points, the roots that will be located on the imaginary axis. So the example that we did for step number 3, the system that we used, 1 plus GHS, this system, we're gonna work on this system again for step number 4, and we can write down s plus 2 s plus 4 square plus ks plus 1 equals 0 from that 1 plus kgs equation. And from this we can expand this and make the polynomial. This will be the final polynomial. Then we're gonna use Routh-Hurwitz's array method to figure out what will be the value of k for which you will get a critically damped system, that is, you will have roots on y-axis. So we created the array, calculated the value of b somewhere over here. You can calculate it yourself, I guess. I believe this is the value, 288 minus k over 10, and then over here is k, then c3 is here. Let's see, c3 is 0. Okay, so now let's see what it is. Okay, so this is s square, and that means this is a quadratic equation. This line is going to create a quadratic equation. Now if c3 is 0, that means we have a marginally stable system where b3s square plus k is equal to 0, and it will represent the point of intersection on the j omega axis. So if we move on, again, this is one of the things that we discussed in when we were discussing Routh-Hurwitz system. So if we have all the elements in one row 0, that means your system is critically stable system. So we go ahead and created the quadratic equation from this. K square minus 156k minus 9216. That's a C3. Let me go back. What do we have here? 288 minus k over 10 is this. So if I do 288 minus k, let me see where it is coming from. Oh, this is C3, sorry. Yeah, we are calculating C3. So we are calculating C3, and I believe, I don't know which value is C3. I'm assuming this is my C3 over here, but you can calculate C3. And then you can figure out that C3 will be equal to this. And if C3 is 0, that means your system is going to be a critically stable system. So from that you can figure out the value of k for which C3 is going to become 0. There are two values of k. One is negative, of course. Value of k cannot be negative. It's all positive values from 0 to infinity. So we're going to take this value, positive value, and then we are going to put that in B3 over here. And when we put that in B3, we're going to get 8.63. And now with this 8.63, we're going to create the polynomial over here. So 8.63 s square plus 201.69. 8.63 s square plus 201.69, which is the value of k. And from that, the two roots will be negative, positive, negative, j 4.834. So these two roots right here, where the curve is going to go along your asymptotes and cut the y-axis, are j 4.834 and minus j 4.834. and this is how we're gonna find where the root locus will cross the y-axis or imaginary axis.